All right, welcome everybody. Glad you're here. I'm Dr. Andy Lovelace. For those of you who don't know me, I've been in the department a long time. I think it's 20 years. I'm a teaching professor, which means I teach a lot of big courses. Um, these review sessions are something I'm doing on my own, but I'm looking for a positive way to connect with students and help direct students. I have a lot of resources and I just want them to be used. And I'm hoping if this is a popular thing, I can convince the department to sort of have this be something on the regular that we do, um, is my hope. Okay. The other things is I'm advertising my resources, but also I'm advertising my courses. I'm teaching Math 126 in the spring, which doesn't help any of you, but I'm also teaching it in the summer in an online hybrid format. And so I hope to have a lot of you take that course if you're around, or if you can take it hybrid this summer. 126. Okay. So I'm not your instructor. Your instructor will tell you what the exam covers, will tell you what to emphasize. But I'm going to talk about the typical things that are there. And I'm going to go through, ultimately, we're going to spend a good chunk of our time touring an old exam. So I'm going to grab one of my old exams and we're going to kind of talk through it. But before I do that, I want to point you to a few other things because no matter what, we're not going to answer all your questions. And so I have a lot of materials, but I'm trying to get it so it's more easier to navigate um, to help you out. All right. Several of you came to the first one of these. I know you've had an exam since then. I did talk to one of the Math 124 instructors, and they said the exam one didn't go that well. I hope it went okay for you. And I hope exam two goes better if the first one didn't go well. So I think I already asked this, but maybe before I jump into materials, which topic are you most worried about? Which topics do you definitely want to see today? Related rates. I'm just mostly confirming um, trying to confirm what I think is going on. So let's do draw. So I've seen related rates. Lots of comments on related rates. Parametric. Okay. Logarithmic. Implicit. A vote there. Just going to, I see another parametric. Some mention of related rates. Lovely. Second derivative implicit. Is Collingwood teaching this quarter? I saw that on one of his exams. Vertical tangent lines. Linear approximation. So linear approximation, I do owe you, I don't owe you, but I do plan to make a video on that. I forgot that I had not finished that part. So let me say what I mean here. So that's great. Okay. Gotcha. So what I'd like to do before we get into those things, I just wanted a sense of where we would like to stop as we tour along. But I've been here a long time. If you used to be that, so we used to have individual, before Canvas, we had individual web pages, and I kind of left mine there, but more as materials. So if you do, I'll share a few things in the chat here. So first, my general page. So I left this here because a lot of stuff that's in Canvas is behind a password or something. So if you click on Math 124, it's not quite as polished as other things. And I plan to redo a lot of this the next time I teach this course. I had asked to teach 124 next year, but I think it's not going to work out. But I have like an exam two review. I have particular things if you need practice, parametric tangent line practice, derivative practice and solution. So there's a lot of stuff there. If you're struggling with a piece as you move ahead, optimization, things in the times that lecture notes are maybe a good place if you just need. Can you hear me? Okay. That happened in the last hour. My mic seems to be not working that well. It probably sounds different because I'm on the mic that goes with my webcam. I have three mics, so we have backups. Does it sound a little different? Maybe. I don't know. Now I'm touching it. Something's going on with my really nice, expensive Yeti mic. Occasionally it kicks out. So I got to think what to do on that. All right. Glad that we had a solution though. So briefly, I was saying this is a good place to check. Lecture notes are good to check. In a moment, I'm going to be looking at old exams. I'm going to focus on mine simply because I don't, posting videos on other people's exams. But if there's particular topics, we can try to hit those. But mine have full solutions. These honors ones may not be the best to study because they were a little more challenging, but if you finish everything else. Okay, so, all right. So last thing, I'm going to point you to, this is new. And so the main reason, one of the reasons I'm doing this is because no matter what, I'm not going to be able to hit all your questions. So I've been making videos to go with my content. I've been doing that for about 9 months and it's starting to really grow. So in the last week, I put together this web page just to kind of help organize people a little bit. And so this is a place to go. Right. And in the earlier this week, I started to put together review videos and I intend to make them for all the courses just so that we can always use them. Because some people I know want a more thorough review. So I made an exam 2 review series here. The direct link to this is this. And if you click on, let's see, this is Calculus 1, click on exam 2 review. You'll see this guy trying to talk here. This is the first. I have this idea. I've done this a lot where I work through old exams, but this series is by parts. So I do a little bit on each of these things. So if you like, when you get to the end of this video, it leads right into the other one if you want, or you can just click on playlist and go here. So this is the main takeaway as I just want this to be used. You can click on Math 124 prep. You can go down to the playlist and I have a thing on each of these pieces. That was exam 1 review. So I'm trying to put together something that would be helpful in the long term. So there's derivatives, just practicing derivatives. There's parametric, there's implicit, there's related rates. So I do already have quite a bit of stuff. Some of them are long. I apologize. You can double the speed. They do have timestamps. You can skip ahead by example. You can pause and try on your own. So this is something I'm trying to do just to take the load off of all the instructors in our department when we have to rush through something. Here's some extra stuff. It doesn't replace studying on your own and working through old exams, but I hope it adds to things that can help you. All right, so that's the plug. My real goal is that I have a lot of stuff I want to talk about, and I think it's kind of cool. So if you want to do like these little projects, I hope this leads to interesting projects. I'm not a researcher, but I'm hoping this is a way that I can connect with students in a positive way moving forward. And I tend to try to teach some classes on these things, and I hope students find some interest in some of these topics. Maybe we can do some undergraduate research or something. I don't know where it's going to go, but I've taught calculus for 20 years. I'm ready for something more fun for everybody. Calculus is fun, but do you say calculus is fun? Oh no, everyone just logged off. All right, so here we go. Let's kick out of that and come back. So what I think is a good use of our time, I've tried before in these review sessions to just open up to questions, but then we end up doing the most obscure questions from the last 20 years and everyone leaves in tears. So I'm going to point us towards a particular old exam, and then we're going to kind of talk through it and tour it. This is the way I would study if I was a student. My studying would start with me opening up like 2 or 3 exams and looking through them like in 10 minutes and making notes of which ones I didn't know how to start. And then I would go back and do a few exams in detail. I think both of those sorts of studying are important. Because over the years, I've noticed students will say, I studied old exam. I got stuck. I spent 3 hours on one question while I was studying. That's probably not a good use of time. Okay, so let's look at something a little older because briefly, this is the review sheet there. This is the review sheet from the last time I taught the course. That course, we did have 4-1 on the first exam, the second exam. Parametric, I don't know that speed with parametric is still involved. I know these derivative rules are definitely there. Those derivative rules, these ones that you got from implicit. So this is really an exam on derivatives more than anything else. But we also have a few other things. Think critical numbers and max and min. That's part of chapter 4. Okay. Let's look at winter 2013. I didn't really prepare. We're just going to kind of peek through an exam of mine and see where that takes us. That's the plan. At any point as we go through this, I will have points where I stop and ask you to give me some feedback. Anyways, so here we go. Thank you. Oh, that's fall 2017. This particular one is winter. Let me grab the link here. Yeah, winter 20, this one. Here. Did it work? Oh no, it's right. You're right. I don't know why I doubted you. I was just reading it wrong. Okay, so let's go. Let's look at this one. It's a little fuzzy. Sometimes when I print it onto OneNote, it does that. Okay, so here we go. Straight derivative question. If these are really different than what you're seeing on your instructor's exams, let me know. We could spend more time here or there. But I'm kind of curious. It's been a little while. I tell students when you're doing calculus, we write things in an ugly way so that our rules apply. So my very first step might be to write this, x to the negative 2 plus 1. That doesn't make it look any better, but it does lend itself better to calculus. And this is actually a really quick question. So what is this question testing? Which rule is this really about? Starts with a ch, it ends with an ain. Yeah, so this is a fairly quick question, so I can just write the answer kind of as we go. You walk up, the first thing you encounter is this function on the outside. You pretend the rest is not there. You do cosine of blah. Then you copy down the inside. That's the most important part of the chain rule, is that you copy down the inside unchanged, and then you erase and go again. Derivative of secant is kind of an unusual one. I just did a 125 review, and they had to do the derivative of secant a couple times in that. So you are going to see this again. So it is something to commit to memory. You do get a note sheet, but it's secant tangent. So this is going to be, come on, secant tangent. And then you leave the inside unchanged. It looks funny because there's two insides. Then you keep going, times the derivative of that. All right, so negative 2x2. Then what goes right here, just to see if you're still awake? You got it, negative 3. So that's all that is kind of a straight bit of derivative work. So I think we'll move forward because I want to continue this tour. And part of what you're learning is how to write functions, how to decompose functions, how to realize that that's a function inside of a function inside of a function. All right, let's keep going. Good, thumbs up. Can I move forward? Seeing if I can see thumbs up. B looks a bit weird. Okay, let's look at B. Sorry if we got rid of that. B looks a bit weird, sure. Part of the reason it looks weird is you're having to learn, a side thing you're learning is conventions. And so one thing I want to comment on here is you do need to know what that means. It's an unusual notation. It's an abbreviation of something else. And that means sine of x to the fourth, which is important to recognize because you need to realize the fourth power is actually on the outside. So a calculus student, once you know this, you don't have to rewrite it, but a calculus student would see this as e to the 5x plus sine of x to the fourth. So there's a lot of this writing things in a way. Yeah, that's the piece. Then we start to look at it. The process for taking derivatives is if there's a bunch of pluses and minuses that completely separate your terms, you do them each separately. There is a plus here, but it's trapped inside. So I have a big mess here. And so the question becomes product, quotient, or chain. So when you have a big mass of variables all mixed together, you basically figure out which rule is the overarching thing. And what I mean by that is, can you take the function and think of it as a function times another function? Can you think of it as a function over another function? To me, it does not look like a quotient rule at all. So I can rule that out, right? There's no fraction in there. Doesn't look like a chain. Now there is something trapped inside of something else, but the question is, can I say it's all trapped inside the same thing? There is a log of a big thing, but can I say that the entire thing looks like that? No. So the first thing I do is not going to be the chain rule. What's the first thing I'm going to do? The product rule. So that's the decomposing your function. This is a function times another function. You cannot write it as a function inside of a function yet, but you can write it as a function, first function times the second function. The second function just happens to be a huge mess. Okay, so that's the decomposing of a function. And then you don't worry about the huge mess. You just start applying the product rule. So it's going to be first times derivative of the second plus the derivative of the first times the second. And I know a lot of the questions are about related rates, so I don't want to spend too long here, but this is going to be x cubed. The derivative of the first I'll do, 3x squared. The second I'll do. And then you say, I give up. I'll take partial credit. No, then you have another job to do right here. And so you restart. So this is how it works. You identify the form of your function, you apply the rule. In the process of applying the rule, you often have a new job to do. And you just restart. You go, okay, for this new thing I'm doing, product, quotient, or chain. Now what's the answer? Chain, yeah. Everything is trapped inside of a log. This is a log of blah. How do we take the derivative of the log of blah? So this is a good skill to be able to analyze and deal with functions. It's 1 over blah. Yep. So the next thing I'm going to write is 1 over blah. But the blah is that huge mess. E to the 5x plus sine of x to the fourth times, and now we've taken care of that. So this is just sort of, do you know the process? I don't know that I'd write a question like this anymore because I would hate to grade this. Okay, the derivative of the inside, I'm going to put here. I just did a bad job with spacing. So the derivative of the inside is e to the 5x times 5. There's another chain rule. Yeah. Well, back then we graded on paper. Something about grading this in Gradescope makes, I don't know, hurt your eyeballs. What would I need? You don't need to write all that stuff I was just writing. It's just me explaining. So I'm almost done. That's going to go there. But what goes right here? Just to see if you're with me. And it's terrible because I've written so poorly. The derivative of sine, that's correct. What's the derivative of sine? Thank you, William. Let's leave the derivative page just for a moment. There's another derivative here. You're going to need to remember the derivative of arctangent. What do you do with the constant to the x? That's so let's do this first. What is the derivative of e to the x? Could you go quickly over how you got 5e to the 5x? Why didn't we do this? Wonderful. Okay. A couple good questions here. So we're just going to pause for a second. So let's talk about functions. X squared, x cubed, x to the fourth. Those are polynomials. And you know those derivatives probably pretty well now. So let's just talk about those. All of those are situations where you have the variable is in the base and you have a number up here. Those are power functions. So x to the n, I would call a power function. The variable's in the base. And you know the rule. The rule is subtract 1 from the power, bring the power down, and subtract 1. That's 1. It's very separate to have an exponential function. Exponential functions are things like, let me just zoom a little bit, give myself some space to work with. E to the x, 2 to the x, 3 to the x, 4 to the x. Yep. What are those derivatives? Now, we almost never see 2 to the x, 3 to the x, 4 to the x in calculus because we much prefer e to the x. Why do we prefer e to the x? What's its derivative? E to the x. It's the special number. In general, the rule for a to the x, this which is called an exponential function, is a to the x, and then there's a little adjustment. It's the natural log of a. In fact, that weird number e, 2.71828182, that's as far as I know, comes about precisely because of this. It's the number that when you plug it in, you get a 1 next to this. So, and I made a video of the history of E, which would give you a lot more background if you wanted. That's on my page. I'm trying to make little videos like this for somebody that we would never do it in class because it would confuse people. But if you want to know a little more, I have that. So those are exponential functions. Okay, so back here when we had e to the 5x, where does the variable exist? Is that an exponential function or a power function? Is the x in the base or is it in the exponent? This is an exponential function. Okay, so there's a big difference between them. So you will never do this rule when the variable's in the exponent. Does that answer your question, Vidi? Sorry if I'm saying your name wrong. So the derivative, you're going to do this like, yeah. So you're going to do e to the 5x. That's basically, the 5x doesn't change anything. It's just like you have a blah there. That's the derivative rule. Then the chain rule tells us what to do next. Whatever is sitting here, we're going to write here. Then we put a little dot for multiplying. That's the chain rule piece. And then we do the derivative of the inside, which is 5. I personally would put the 5 before because I'm just worried I'm going to mix it up. Okay. That also answers, who was asking the other question? Hopefully that also answers, I think somebody was asking a question about 5 to the x. Yeah, the derivative of 5 to the x is 5 to the x log of 5. So we hit a couple things there. All right, let's move forward. Kind of a slow tour we've got going, but so then I have a question here. Well, this builds off of what I just said a little bit. And I want to leave time for related rates. I know that's a question people want to do. If I'm too slow, you can watch the recording later. I won't put timestamps in the recording. I do have timestamps in the prepared videos. I just don't want to edit the recording. It takes too long, but you can speed through it. Okay, consider this problem. Find the equation of the tangent line. Really, when the word tangent appears in any of your calculus courses, you're going to take a derivative. So if you've forgotten this piece, let me say something about tangent lines. The recording of this video I'll put directly on my YouTube channel when it's processed. I'll put it in that playlist. 124 exam review playlist. Yep. Okay, so the moment you see tangent line, I would write this. Blank. The question is asking you for these three numbers, and they tell you one of the numbers, 1. So we need the height at 1, and we need the slope at 1. The tangent line is just an opportunity for us to use those things. So the height at 1 we can get. I mean, this is a weird function. This is when we need calculus. Calculus is good for analyzing functions. It really helps us when we have a weird function. So the height at 1 is 4 to the square root of 1. And what is that? Just seeing if you doubt yourself. 4. Yeah, we're going to put 4 right here. So again, don't be scared by tangent line questions. They're really asking you to take the derivative. But the reason this builds nicely on our last question is this a power function? Well, the variable's in the base. Or is it an exponential function? Well, the variable's in the exponent. This is as bad as it gets. You can't use either rule. We're stuck. Maybe we write this as x to the 1/2, but that doesn't help very much. We're just stuck here. We can't use the power rule because there's a variable in the exponent. We can't use the exponential rule because there's a variable in the base. We need some way to get out of this problem. And what is that way? There's actually 2 ways people present it. So I guess it's going to depend on your instructor. There's a certain technique. Yeah, logs. Logs do a good job of turning exponents into multiplication. There's a trade-off for doing that, but we're going to take the natural log of both sides. Natural log of y, natural log of 3x plus 1 to the x to the 1/2. There's this one log rule that you really, really need to know. And it's not just for this, it's for every time you're solving. Like if somebody says 2 to the x equals 10, and you take the natural log of both sides, you also use this log rule. So it's by far the most important log rule. And the log rule is, what do we do with log of a to the b? And the answer is we yank this down. It's one of the exponent rules in reverse. So this becomes the log of y equals x to the 1/2 times the log of 3x plus 1. That's the method. So that gets rid of the initial problem, which is that we had a variable in the base and the exponent. Is that all right? Questions on that piece? With me there? Thumbs up, thumbs down. Okay. There's a reason we aren't scared of this, because we have a technique that allows us to differentiate even when y is not by itself. And that's an important technique. Oh, what just happened? I changed all the colors. Didn't know I could do that. There we go. Okay, and that method is to differentiate directly. And this is really important. I mean, you will encounter this a lot. I mean, if it not only is it helpful here, it's just practical. My favorite example is always a circle, because rather than if you solve for y in a circle, then you're going to have to use square roots. So if I have to differentiate, I would just differentiate directly, which is way faster. So there's a practical side to this, but it requires that you can think about a variable being a function of some other variable. It's about the roles of your variables. Okay, so back to this. I'm trying to compute dy dx, which means I'm treating y as if it's a function of x. So it's like there's a function trapped in there. And so we're just going to use the chain rule. Okay, that's it. So we're going to differentiate both sides. The key step is this becomes 1 over blah, which is y, times the derivative of y, which I don't know. So we just write y prime. Why does 4 to the square root of 1 mean? It doesn't mean y is 1. It means this is 4 to the 1, which is 4. That went here. Am I with you, Ella? Somebody's giving me a private message. Sorry, I was looking at that. Yep, good. Right here, I'm going to have y prime or dy dx. That's the key moment. That's actually implicit differentiation. And then we switch to how in the world do we take the derivative of the other side? And what do we do? Product, quotient, or chain? Product, yep. First times the derivative of the second. This is going to be a mess. 3x. Here, I'm going to intentionally make a mistake. All right. And there could be an unintentional. I don't know why I'm getting crooked here. I'm a little tilted. All of a sudden, my writing is going up to the right. X to the negative 1/2. I don't usually do that. I think it's how I'm oriented on I have a little thing I write on here. But it's pronounced. Okay. That's it. But I made a mistake. Does anybody spot the mistake? Yeah, I needed to take the derivative of the inside here. There should have been a 3 here. I personally would write the 3 there. Now, a small comment about this question is it doesn't ask me to simplify. If you remember what we're being asked, we need to find the slope when x is 1. So this is just a bit of advice I always have for students. This goes for sort of all your classes. If you need to compute a value of a derivative, you can't plug in that value until you're done differentiating. If you plug it in earlier, you just get 0. But the moment you're done taking the derivative, then you can plug it in. And in this case, that would be a lot easier. What do I mean? Well, I know this is 1. 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 I also know what y is. What's y? We already computed it. When x is 1, what's y? 4. That's way easier. Let's try to, I'm going to turn my pad and write straight up and down again. 1/4. Uh-oh. Now I'm turned the other way. It is because of my pad. All right. Somehow I bumped it when I was messing with my mic. Ah, that's the reason I was doing that. I get it now. This is going to be 1 times 3 over 3 plus 1 is 4 plus 1/2 plus, not plus, there is no plus, the log of 4. Ah, now I know why I was crooked. Okay, that's what I did is I plugged in a 1 for all the x's. Your goal is to get dy dx, so it's going to be multiply everything times 4. Actually, if you multiply everything times 4, I think it comes out kind of nice because the 4 will cancel with that 4, and it'll make that a 2. So I think you're left with 3 plus 2 log of 4. It's not that pretty, but okay, so there's logarithmic differentiation, which is really implicit differentiation. Let's keep going. And we can go out of order here. We have a parametric. The key point about parametric is dy dx is dy dt over dx dt. It's a clever use of the chain rule. But I want to check my time here, because a lot of people want to talk about related rates. So I might kind of zoom forward. Let's speed up our tour. We have an implicit problem there. So we're going to have to differentiate with respect to x. We can come back to that. We have a Larry Bernandez problem. If you don't know who Larry Bernandez is, you'll have to look him up. He throws a baseball. This is a parametric problem. Parametric, okay. Related rates. We've done it. So since there's a lot of questions about related rates, and I tried to very carefully make a video about related rates. So if I don't hit your topic here, there's just a few things to say. So let's read this one. Let's go here, and then if we want to go back, we can sort of after this problem, I'll start taking questions. Cool. At time t equals 0, a balloon is released from the ground from a point P, which is 332 feet away from you. You're walking towards the point P at a constant rate. It's a lot of information. So you need a little bit of a plan when you're approaching these problems. So we're going to talk about that plan in a second, but let's finish reading. Balloon is rising vertically at a rate of this. At what rate is the straight line distance between you and the balloon changing when the balloon is exactly 400 feet high? Okay. So let's think about this. I don't have the solution in front of me. You're going to have to help me. This fits nicely into how I think about all problems, which is what are we given and what do we want? These are sometimes the hardest questions to answer in real life, but on a math problem, they're usually easier. But we need to answer those questions before we can move forward. Going with that, it usually helps to label everything. Label as much as you can. So those are things I would do on a second reading of the question. So at times t equals 0, a balloon is released from the ground from point P. I feel like there's several things I would like to label. Okay, how about, and there's no correct or incorrect labeling, but I'm going to call this X. I'm going to call this length Y, and by that I mean the distance from here to here, the distance from here to here. I don't know why my arrow got so short all of a sudden. And I think I'll call this Z. And I don't know what else to label. I mean, you could label this alpha. You could label the area. I'll have A be the area. You could have P be the perimeter. Now, a lot of this is a huge waste of time. But the point I'm making is if you're unsure what to do, label everything. You should really only label things that are mentioned in the problem. Okay, that's step one. Label everything. Now I'd like to go through and figure out what they gave me. So a balloon is released from the ground from a point which is 332 feet away from me. So initially, the next question which might be good is X changing in this problem? How about we read that and I'll let you think about that. Which things are changing? That kind of goes along with labeling. Is X changing? If you were to watch this scenario. So what does it say? Yeah, because I'm walking towards it. Maybe I should have put that in there. That would have helped. Or maybe I'm sad because the balloon's going away. I don't know. But it said I'm walking this way. So I think they're all changing. X is changing. Y is changing because the balloon's going up. Z is changing. Oh no. Theta, I think, is changing. Alpha is changing. The area is changing. Everything is changing here. All right. So that's just kind of a deciphering of what's going on. If you don't know if something's changing, just leave it labeled as unknown. You might be making the problem a little harder on yourself. Okay, so let's now decipher the information. And sometimes you can go out of order. At what rate is the straight line distance changing? Sometimes it's easier to answer this question first. So what do we want? At what rate is the straight line distance changing? What is that? You can type it in. dz/dt. This goes for later in the term when you're doing optimization questions. It's often helpful to recognize what you want. We want that. And then they gave a little bit of information when something is 400. What's the something? I'd like to know dz/dt when the balloon is 400 feet high, when y is 400. So even if there's a lot of information, that piece, and the reading is part of the math. Sometimes people say, if I knew which formula to use, I'd be able to do it. But we got to practice that reading. Okay. So that's how we needed to label first. Now what was given? You are walking towards the point P at a rate of 4 feet per second. Ooh, what does that tell me? We're going to keep it exact as long as we can here. But let's see, we're not there yet. So what does this 4 feet per second tell me? So now I'm trying to figure out what I was given. Dx dt. Is x getting bigger or smaller? If you were to draw this picture, it's getting smaller. So dx dt is getting smaller. How do we write that? -4. Every second we're losing 4 feet. Okay, so I'm just tracking through the information they gave me. A balloon is released from a point 332 feet away from you. You're going, what else do we know? The balloon is rising at a constant 500 feet per second. And you can see where I'm breaking it up in a way that I don't have to hold everything in my head at once. I labeled everything. I identified what I was given. I'm not going to even let myself think about the question until I've written everything out. Okay, 50 feet per second is how fast it's rising. So y is getting bigger. So dy dt is 50. Okay, I think we're in business now. So that's the part where you probably should slow down and think about a little bit. But what are you given and what do you want is your guiding principle. All right. And I do have kind of a review sheet on this where I like my review sheet. So just a brief moment so I can show you something. Made this a long time ago. Where is it? Oh, related rates is 3.9. I hand this out the day we do this. So if you want to process, label everything. I now say, what are you given and what do you want? I used to say, what do you know and what do you want? And then here's everything you used in the homework. All right. Related rates review. Let's throw that in here. Okay. The moment I have that, this tells me what to do. The idea of related rates is actually kind of simple in the sense that it says, if you know the relationship between the quantities, you immediately know the relationship between the rates. So I need a relationship between the quantities, and I'm not going to use theta and alpha. I'm going to use these variables because these are the variables that I'm given, and this is the variable that I want. So now let's articulate the question. Yeah. Oh, I did it privately. I shared it privately with Ella. Sorry, Ella. Yeah, because you gave me a private message, it only went to the one person. Okay, so if I want to articulate what I want an equation that has x, y, and z in it. Most importantly, I want z in it. But can you come up with an equation that has x, y, and z in it? Yeah, it's the Pythagorean theorem. That's not the only one. I mean, you could almost draw any equation that's true. You could even use theta, but it's kind of a waste to use theta if it's not involved in the problem at all. So x squared plus y squared equals z squared. The moment we have that, we're done. Why do I say we're done? So the main thinking here is all three of these things are changing. So we actually have a formula for x. We have a formula for y. We can even find the formulas because they're constant rates, but that would be kind of extra work. And we would like to differentiate with respect to t. So here's what's actually happening. And we know how to do that because of implicit differentiation. It's not quite as bad as it seems. So we're just going to differentiate this. The 2 comes down. It becomes an x to the 1. And then you do times the derivative of the inside. The derivative of the inside is dx dt. What am I going to write next? I'm getting a little crooked. can see it happening. Yeah, I'm going to do 2y dy dx, 2z dz dx. This will be interesting to compare with something you'll learn in Math 126. But in this situation, all of the variables are changing. Nothing's a constant. So it was kind of a race to get to here, realizing what the variables were that were important. But the moment we had this, we differentiate. And at that moment, we're done. It's dy dt, though. Yeah, I might have said the wrong thing. But they're all with respect to t. Yeah, thank you, Elise. All right. I guess if it was me, I would divide everything by 2. Okay. And then I'm going to plug everything in. You don't want to plug any numbers until you've actually taken the derivative, because if you plug in numbers before you take the derivative, you're going to get a bunch of zeros. You sometimes have to plug into both, as you've seen. And you know that your goal is to get this. So having the plan really helps me. You can see when I do this problem, I'm not worried. I know there's a ton of information. The first time I read it, I'm like, what the heck's going on? But I just do the process. What am I label? What am I given? What do I want? And that really helps me. So what do I know here? I know that y is 400, so I can replace this by 400 and this by 400. I know that dy dt is 50, so I can replace this with 50. I know that dx dt is -4. But I seem to be missing some things. At what rate when the balloon is 400 feet high? It takes 8 seconds to get there. Oh, there's a little more stuff I have to solve. Do I have enough? Anybody have any ideas? And I just happened into this problem. You can see I didn't prepare. What else do I know? I do know the -4. This is slightly trickier than I expected. You can find x by plugging in 8 seconds. Yeah, that was the hint in the problem. I needed my own hint. We want to know what happens 8 seconds from now. And we actually know you started at 332 and then you walked for 8 seconds. I know that's a little tricky. I don't know. So what can I say? If you start at x is 332 and you decrease it by 4 feet every second, what can you do? I did divide everything by 2. You can put it back in though, if you want. Doesn't change anything. Yeah, thank you. So -4 times 8. 8 seconds of this will subtract 32, so it's 300. If I was going to guess, I would have known it's 300 because I know I wrote the question. If I'm going to give a question like this, I'm going to make the numbers nice. Why is 300 nice? Well, because if it's 300, this is going to be 500. You can solve for it, but then we plug everything in and we get it. So there was this added piece that at the very end there where we had to figure out, okay, I know where this is going to be in 8 seconds. It'll have gone up to 400, but where will that be in 8 seconds? So that was an added complication. Summarize that last step. So yeah, the play, everything was kind of running smoothly until I got right here. You with me to there? Elise? Let me erase all this. So we had all the pieces, we took the derivatives, we plugged in the numbers they gave us. Yeah. There was then this challenge. And this was the challenge. This is probably the hardest part of this question was right here. He went, I am missing stuff. So let's articulate what's going on. I don't know what X is at this moment. I don't know what Z is. So how am I going to finish this question? Because I can't plug those in. And I know that I'm trying to get this. But what did they tell me? They told me that, and I don't know how the best way to say this is, but they told me initially I was at 332 feet. And then every second, what was happening? I was going, and I probably should have labeled this. That would have helped us a little bit. And going 4 feet per second this way. The balloon started here and was going up, and it was going 50 feet per second. And normally I'm out of practice. Normally I do label that. It's been a couple years since I taught this course. So this little hint says in 8 seconds, the balloon is going to be up here at 400 when the time is 8 seconds. So the question is 8 seconds later, where is this going to be? Does that help at all? Where's the 400 coming from? Well, if you go 500 feet per second for 8 seconds, you're going to be at 400. If we started walking at that same moment, it's going to be 4 times 8. 4 feet per second times 8 seconds. That's 32 feet. And so we've walked 32 feet this way after 8 seconds. So what will X be at that moment? 32 feet less than 332. Does that make sense? Yeah. That was a sneaky little bit to finish the question. So I might have just had to take partial credit. Normally you write your equations, you plug everything, you have it. This had this extra challenge of, why do I know what X is? But then when I knew that X was 300, I then knew that 300 squared plus 400 squared is Z squared. And that's going to give me 25,000. I better be careful with my zeros. But I can then compute this number and hit the square root button. And that's going to be the square root of that mess, but that turns out to be 500. Only reason I know that is because 3 and 4 give a very nice triangle. It's the 3, 4, 5 triangle. So that's how I was trying to just quickly jump past this, but that was a bad plan. So this is 300. You plug it in. From that, you can solve for Z, which ends up being 500. The point being that typically in these problems, it's a matter of plugging into both these until you get what you want. There are these moments when you're like, it feels like there's not enough information. Let's try the next one. Let theta be the angle of inclination between your line of sight. It says, see the picture. Can I confirm the answer? Oh, what is the answer? Good question. I focus too much on that. dz dt. Let's cancel those 2's like I wanted to do. The z is 500. And so it's going to be 300 times -4. So -4 times 300 plus 400 times 50 all over 500. And let's play the following game. Let's show this. Old exams here. Here's the problems we've been doing. And that's what we got. I guess I did it the same way. So 37.6. Yeah, great. Well, I should have just had you all post. I'm out of practice with this. Okay, so now we have a new one. Let's sort of play the game of what are you given and what do you want. So same picture. This is theta. This is x. This is y. This is z. And it says at what, so what are we given? And what do we want? And I think that information up there hasn't changed. So we still know that, sorry, I'll scroll down in a second. I'm just copying down some information. We know that this is -4. We know that this is 50. Okay. At what rate is theta changing? So at what rate is theta changing when the balloon is 400 feet high? And since 400, I think, was the same number as the previous part, I'm going to zoom out for a second. You could also use the other information. So we also know the dz dt from the previous part, which is the mess we just found at 400. Okay, that tells me what to do. So in this case, I wouldn't use dz dt unless I had to because it's a messy number. I'd rather use these variables. So now I can articulate what I would like to do. I would like an equation that has x, it definitely has to have theta, some relationship that has theta and x or y, and it could also have z. There are a lot of correct equations for this. I can think of 6 immediately. Cosine of theta, sine of theta, tangent of theta, secant of theta, cosecant of theta, cotangent of theta. All of those would be appropriate next steps. But yeah, so you just need to write something that relates those sides. So tangent makes the most sense to me because it involves these nicer numbers. Okay. So that's the thought process. So that's why it's so important to identify what's given and what you want. You go, I would like an equation that relates these things, something that I know is always true. And we got it. Okay, now we need to take the derivative. And this becomes a matter of taste of how we think that's going to go as nice as possible. But once we take the derivative, we're going to plug in our numbers and we'll have it. So for some reason, the way it looks makes me feel funny. Like I would like to move the x. I don't know why I'm having this thought now, but I'm just going to say it. For some reason, I feel like I want to do that simply because I'd rather use the product rule than the quotient rule, but they both work. So let's start differentiating with respect to t here. If you want, you can do this one. If you want, you can try some of the other trig functions. You have a lot more freedom than you think. Students don't like freedom in math, but this is going to, what's the derivative of tangent? Yeah, no one wants freedom. There's a few problems in Math 126 where you have to make a choice and then based off of that choice do something and nobody likes it. Okay, secant squared of theta d theta dt. So if you do this one and you get here, you get to do the quotient rule. Numerator, denominator. And I always remember it alphabetically. Numerator times the denominator minus. You don't have to isolate y. I'm saying that in my head, I was thinking I would have done that because I wanted to avoid doing the quotient rule, but then I would have to do the product rule. So let's erase that because I'm not doing that. Yeah, I'm doing the quotient rule. I think Professor Camacho has a funny way to remember this. I just remember it alphabetically that D comes first. Denominator. And then I just start filling everything in. I tell students to fill everything in that requires no brain cells, meaning the things that aren't derivatives. So I do y, I do denominator squared, and then I tell them to do a visual check, denominator squared, numerator. And then we have a couple derivatives to do. The derivative of the numerator is dy dx. What's the derivative of the denominator? What goes here? Yeah, some people like to rewrite this as y times x to the -1 and then do the product rule. That's also perfectly fine. Many paths lead to Rome here. What made me think of that quote? I don't know. It's a 1. At that moment, we have it. You know, if I kind of erase this and just, the answers should be there. So in general, the moment you write down a relationship between your quantities, You take the derivative. That'll give you a relationship between your rates. That's why it's called the related rates problem. And then you plug everything in, and hopefully you have your answer. And at this point, we already did the hard work in the previous part to figure out that x is 300. So do I have it? Let's see. This is 400. This is 300. That's 300. dy dx is 50. Theta, oh, I don't know theta. So that's the only piece I don't know. But there's another place I can plug this stuff in. This is 400. This is 300. So let's kind of summarize where we're at. Take a step back and say, I know that tangent of theta at this particular value is 4/3. Oh my gosh, I made a critical mistake. That's why nobody was talking. Oh man, I forgot. I shouldn't be laughing. Okay, so this is dy dt. And what should go here? Now say it. Dx dt. I don't know what happened there. My brain went somewhere else. Something didn't look. Oh, shoot. Sorry, everybody. Okay. Dx dt. I need to put more space between the reviews, is what I'm learning. All right. I know this is 4/3, and I know that secant squared of theta, d theta dt, is equal to 300 times 50. I'm just plugging into this. Minus 400 times -4 all over 300 squared. All right. There is a little note. Yeah, the product rule would have been better. That's why I think my instincts told me to multiply by x first, but I didn't follow my instincts. All right, we're getting there though. The there is a little maneuver here, which I'm going to mention because you're going to see it again in Math 125. And it's a way to, you maybe saw this already, but it's a way to figure out what secant is if you know what tangent is without using your calculator. So if tangent of theta is 4/3, well, I might have missed a question. Yeah, because we're doing, theta is actually changing. So basically the rule, if you're the first time you're doing it related rates questions, there's going to be a d theta dt, dy dt, dx dt next to everything you differentiate because everything is changing. But there's this clever idea about trig, which is if you know two sides of a triangle, you can solve for the third side. In this case, it's 5. And once you know 3 sides, you know all the other trig functions. For example, you know that sine of that same angle has to be 4/5. SOHCAHTOA. I didn't know SOHCAHTOA until a student told me when I first started teaching. I'd never heard that before. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And secant is 1/cosine. I know it's weird that it is. So secant of theta is 5/3. So this is just a little trick to not have to get my calculator out. Secant is 5/3. We're squaring that d theta dt. And then whatever in the world this is, 15000 plus 1. You can see how much I hate getting my calculator out. You can definitely get your calculator out. 3090000. And then you divide and see. Okay, maybe it's time we flip over here. That's what I got. I did it the same way there. So hopefully got something out of that. I don't know. This is why I made the separate videos. Yeah, you don't have a secant button, but you get all the trig functions from sine and cosine. Here, I'll show you something. Sorry, I don't know how helpful this is, but I hope the videos you go to after are more helpful. But this, hey, that's not my best review sheet. That's an old one. Where's my better? Oh, it's not on this page. I gotta fix that. If you go to 125, my unit circle and trig fact sheet are here. This is what you need to know about trig. You need to know that tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over. So if you know these, then you only need to know sine and cosine, and you only need those buttons on your calculator. Sometimes arctangent is nice to have. So when somebody tells me, I want to know when secant is something, like if somebody asks me, what is secant of pi over 3? I go, I need to know cosine of pi over 3. What is cosine of pi over 3? It's this x coordinate right here. So that's how I do it. Thank you, William. All the trig values are in that unit circle. Yeah, the videos, everything, I'm going to try, because YouTube is not great. What was the answer? Good question. Let's see. It was a really small number. 0.0664 radians per second. Since we're working in radians, radians are kind of weird because you go once around the circle every 2 pi, which is about 6. So if your angle is changing just a little bit, it's a really small number. Oh, show the work. Yeah, it looks like I did it the same here. Let's go back. Yeah. How did I get to 5/3? I used the fact that this was 4 over 3 to label this triangle. And then from this, I got cosine was 3/5 and secant's 1 over that. All right, Elise, thanks for coming. I can stay for a little longer. We could try to hit some other topics. I'll put this on the YouTube channel. It will be, here, right here. So if you want to navigate to the channel, there's this link that takes you straight to the YouTube channel. It'll be one of the first videos, probably tomorrow, because it takes a few hours. I would put the unit circle on my note sheet. Yeah. It's a really, you're going to need it for a long time if you stick around. So, I mean, well, you really just need this first quadrant, but it helps you remember what the other values are. Yes, if you know these first few values, let me just say something here. It's kind of a combination of things to know. Let's take a brief detour and then I'll get back to some other questions here. But first and foremost, you do need to know your angles. It just gives us a few values to work with: the 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees. Other things, and then to know the corresponding radians. Let me recenter my page because I know I'm doing it small and in a bad color. I did it like that. Okay, it's good to know the corresponding radians. So this is 0, pi over 6, pi over 4, pi over 3, pi over 2. So as I think about moving forward through our math courses, it's good to know those angles and what they translate to in the other quadrants. It's actually not that bad. In terms of pi over 4, it's like working on a ruler. This is going to be pi over 4. This is going to be 2 pi over 4. This is going to be 3 pi over 4. This is going to be 4 pi over 4, and so on. And then we have the pi over 6s. This is pi over 6. This is 2 pi over 6, 3 pi over 6. So it's good to know those, just because when you're asked something like, what is cosine of pi? I think about the unit circle. I go, pi is over here, and cosine is the x coordinate on the unit circle, and sine is the y coordinate. It's how we define it past 90 degrees. So unit circle is really helpful for that, because it gives me a quick way to realize, all right, cosine of pi has to be -1, because that's that coordinate. It's the x coordinate on that. Okay, so the only thing you really need to memorize is the first quadrant, and then you got to know how to work past it. And here's a goofy way to remember it. I always tell students, if you can tell me one value, we can fill in the whole thing. And usually the value it's helpful to know that they're also waves. I mean, there's more than one thing that connects. It's always good to remember something by having more than one pathway to it. I remember this, that the cosine wave goes like this, and that the sine wave goes like that. But I always wonder, is that something you know? That the sine starts at 0 and the cosine starts as 1. That was always my memory marker. And that was helpful for me, and I'll show you in just a second. So that tells me one value right here. You can also just remember that the x value is cosine and the y value is sine. So where does sine start is my question. What is sine of 0? Help me out in the chat. Sine of 0. This is sine of 0. Cosine of 0. Might just, yeah. Cosine of 0 is 1. Sine of 0 is 0. You can also remember that sine starts at 0, whichever helps you. I'll do parametrically next. Okay, if you can remember that 0 and have a little bit of sense of what the others are, here's how you fill the rest in. This is just one weird way to remember it. 1, 2, 3, 4. 0, 1, 2, 3, 4. So you can generate this on a test if you ever forgot. You hit the square root button on every single one of these. Square root, 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 and divide by 2. This is going to give you 2 over 2, which is 1. This is going to give you the square root of 3 over 2. This is going to give you the square root of 2 over 2. This is going to give you 1 over 2. This is going to give you 0 over 2. 0, 1, square root of 2 over 2, square root of 3 over 2. This is 1 over 2. Why can't I write it? 1. So there's a way to remember it, if that helps. Honestly, what I remember is that these get bigger. And if you can order your numbers correctly, now that's a separate question. So I'm giving you many different ways. Sometimes students say, why is that true? But to me, I understand that 1 is smaller than the square root of 2 is smaller than the square root of 3. If you can remember that, then you would know that sine at 30 degrees has to be a half. Sine at 45 degrees has to be square root of 2 over 2. Sine at 60 degrees is square root of 3 over 2. So if you can just remember sine starts at 0, I feel like I can remember all those values. Did that help? I don't know. Yeah. And honestly, when someone gives me cosine of pi over 3, I know that it's either root 3 over 2 or a half. So what I do is I get a coin out of my pocket and I flip it. And if it's heads, I say a half. And if it's tails, I say root 3 over 2. That's not the way to do it. What I do is I think that the cosine, what I used to think when I was a student, I don't know how I remember it now. It's ingrained in my head. But I think about if I'm standing at 60 degrees, which is pi over 3, which coordinate is bigger, the x coordinate or the y coordinate? That's how I used to remember when I was a student. And I could always figure out, well, if I have a triangle like this that's 60 degrees, this number is definitely bigger than this number. So this has to be square root of 3 over 2, and this has to be a half. And that's how I used to remember it. So this had to be bigger. And since cosine is the x value, it's a half. Now that's kind of a convoluted way to remember, but that's how I remembered it. So there's probably 3 or 4 different ways to remember those values. If you can remember those, then you could think about the corresponding angle beyond it. All right. Varshini, did you have a particular parametric? We could look. I had one earlier. Let's look at maybe a more recent exam. I don't know. Winter 2017. It's also good now that we've toured an exam, and it wasn't a very fast tour we did, to sort of look at these and go, what's my first step? Sorry, I don't know why I'm doing that zooming. All right, thanks, William. Thanks for your input. Okay, so derivative, horizontal tangent line means take the derivative and find when it's equal to 0. There's a parametric. So parametric are really important in Math 126 if you continue. As soon as you start studying things in 3D, you have to have parametric. But basically, if we're going to study motion, like if you're looking down on a car moving on a map, then you want parametric. So ultimately, for some people, it helps to think about it in physics terms. We're just going to study the x and y component of velocity. But basically, it means we're going to take the derivative with respect to t. In this case, you're going to get t squared. I haven't read the questions yet, but this is going to be the main steps you do in any such problem. 3 over, so I just did the chain rule. Oh, messy function. Why did I ask this? Log of 4. Oh, I think when you plug in numbers, it'll come out better. Move some things around here. Not using the right part of the screen, you might have noticed, because I can't see it. It's covered by all my windows. All right, here we go. Yeah, we could do another chain roll too. I think we have time for that. A lot of these things we can do kind of quickly. I just was explaining. Okay, so there's my derivatives. We think of this as the vertical velocity. In physics, they might say v sub y. It's how quickly your y is going up and down. And we think of this as the horizontal velocity. Okay, so it says find the vertical velocity. It's asking for this. Now, I can't remember, because the last time I taught this, I think there were only 1 or 2 questions. Do they ask you for the speed in any of the homework questions? Do you want to tell me in the chat? Just because I haven't taught it for a couple years. No, okay. You'll see that when Math 126, it's the square root of x prime of t squared plus y prime of t. But if they're not asking for that, we can leave that. Find the equation of the tangent line. So this is when we're trying to do the stuff we've been doing, but things are given parametrically. So the equation of the tangent line goes like this. You once again need 3 numbers. We need the slope, we need the x value, and we need the y value. How do we get those? And they didn't tell us any of those. What they told us was the t value. They said t was 0. And I need the x value, and I need the y value, and I need the slope. Yeah, the vertical tangent line would be when the vertical tangent would be when dx dt is 0. We'll see that in just a second. So this is asking you to plug in 0 to the x formula. This is asking you to plug in 0 to the y formula. And this is asking you to plug in 0 to dy dx. And that's the ratio of the vertical velocity divided by the horizontal velocity. If we want a vertical tangent line, it's when this is undefined. This is undefined when the bottom is 0. So this would be when dx dt is 0. If dy dt is 0, it's a horizontal tangent line. that all right? Can we do some more differentiation? I think there was a question on that. I wonder, let me just think of something here. Grab something that might be of help. Does that have all the things I want? Okay, let's try this. Just a moment. Okay, I don't know if it switched to this. This is my derivative practice sheet from my website. Here, I'll share it in just a moment. Somebody's asking about derivative practice. So there's derivative practice. And here's the solutions to that sheet. But let's look at these. So let's kind of run through this. I think when I made this doesn't quite work the same as a multiplication table practice sheet. But let's kind of run through these if you have pencil and paper and think about how these go. So are we good with that first one? The log is trapped inside the third power. So when I look at that, I see something to the third power. So it's a chain rule problem. It's 3 blah to the second. And then the chain rule says you leave the inside alone. And then you multiply times the inside. 1 over x, done. What's the first step on this one? If you can read it. It's y equals, sometimes when I print things in OneNote, things don't come out. What's the first step? Take the log of both sides. So you take the log of both sides, you use that log rule, you take the derivative with respect to x, you get 1 over y dy dx, and you do the product rule. And you can see the full solution of that. But the question was about the chain rule. So let's do another chain rule here. Let's just hammer a bunch of problems, if that's all right. Since I know this is something you all need to be successful in the next test and successful in courses that follow this. So here you go. What's that derivative? I know it's hard to type it in, but just try to write down what it is. And that's tangent of e to the x. So tangent's on the outside, so we're going to write down the derivative of tangent, secant squared. Leave the inside alone, times the derivative of the inside. This is just a goofy one. 0. Here we have a couple other ones. So let's see which one of these we want to do. Here's a few. Yeah, thanks for being here. Here we have an implicit problem. The question's asking for dy dx. So if you're asked for dy dx, here are all our variables. Think about what you'd have. So 4x to the third. Unfortunately, we have 2 variables here. So what do we need to use? Probably the hardest part of this, product rule. Yep. So we have first, we have second. So we're going to do first times the second. So x times dy dx plus the derivative of the first, which is 1 times y plus 4y cubed dy dx equals 0. It's going to depend on what the question asks for, but if the question asks for dy dx, then we're going to collect those together and move everything else to the other side. So there's going to be a negative y for moving this over. Yeah, thanks for being here. Negative 4x cubed Take this, divide, and you're done. Okay, so the question was originally about more complicated chain rule questions. This is in the chat a little while back, just a couple up. Derivative practice followed by derivative practice solutions. I'll put it back in there. Oh, I see. You caught me at the end. But thanks for coming, John. I will have a recording of all this. I don't, yeah, the chat doesn't appear later, I don't think so. How about that one? Somebody was asking about chain rule a while back. More complicated chain rule. This might not have been what you meant. But let's try that one. Yeah. So dy dx. So it's really about compartmentalizing here. I mean, if we really wanted to be extreme, we could try to label. We could say, well, we have something trapped on the inside. Let's call that U. I don't find this helpful. I have some, this would just be extra time. We eventually want to get to where we don't have to do this. But we have this. On the inside, we have U equals tangent of, I don't know, V, and we have V equals 2 to the X. We call this a composition, where basically this is on the inside, it's plugged in here, and then that's plugged in here. So we're learning to decompose functions, but really the key thing is what's on the outside. So once you write this function, if you walk up to it, the thing you encounter on the outside is cosine. And so you just start taking the derivative as if that's all you've seen. Like you can't see any further. And the Lovelace law of the C says this. If a function starts with the C, the next thing you're going to write is negative when you take its derivative. I like to call it that because it sounds like I'm a pirate. Lovelace law of the C's. And then you write sine of theta. And that's how we take the derivative of cosine. Then the next step is to copy down the inside. And then erase. Hit a dot and play the game again. So now we're going to do the derivative of tangent of something. So you really have to do this compartmentalizing piece. So you have to go, well, what's the derivative of tangent again? Oh, that's the secant squared. And if you want to know why the chain rule works or the product rule, I actually have videos where I prove those things, short videos, but that doesn't really help you do the problems. Okay, so then we're going to copy what was on the inside, and what was on the inside was 2x. And then we get to play the game again. Dot the derivative of 2x. That cool? That one get you there? This had nothing to do with this question. I just was overlapping. But really, I mean, what we're learning, a valuable thing we're learning is how to break down functions. In order to use our calculus rules, we have to be good at breaking down functions into their pieces. But that's a pretty good skill. Are there any other big chain rules here? Ooh, 13 looks terrible to me. I wouldn't like to do that one. And then 15 is a chain rule question. Oops. 15 is confusing simply because of the notation. So maybe we'll start to wrap up, but what's on the outside of this one? Is it the cosine or is it the square? Number 15. What's the most outside function? The square. That's not something you see in the picture. It's something you have to know about math notation. that this means this. And it's very standard. So it's not us trying to trick you. It's just how it's typically written. But you have to know the square is actually on the outside, and that matters for the chain rule because the derivative, the first thing you're going to do is however you take the derivative of a square. Sometimes this looks funny because when you take the derivative of a square, the new power is 1. And oftentimes what happens is when someone writes, then they try to copy down the inside, it's easy to get lost and think you already took the derivative of the cosine, especially if you don't write this power. So I've seen this happen a lot where someone kind of gets stuck here and then they just take the derivative of cosine. So this is a common error here. Let's see if you can spot what they did wrong. They did the derivative of the outside correctly, but they skipped a step. So if you sort of break this function down, inside was a cosine, then inside of that was a sine. So there should be 3 chains, 3 links in this chain rule. So I should have been doing the derivative of cosine. Now this is unfortunate because it's going to be negative sign. I don't like to put a negative here because it looks like I'm subtracting. So I've kind of gotten in the habit of putting my negative out in front. Because I find if people put times the negative, then later they get mixed up. Then the inside stays the same. Times cosine. Part of the problem is sometimes the answer just looks so weird that we convince ourselves it's not right, and then we erase a correct answer. I see that a lot too. Here's a weird one, 27. Or do we want to do anything else? I was just looking for the weirdest extreme chain rule problems. Oh, linear approximation, thank you. I just made the chat vanish on me. Maybe 27 first. Okay. 27 is y equals, this means arctangent. Different instructors have different preferences of how they write this, but you really need to be comfortable with both notations. So these 2 things are the same, arctangent and inverse tangent. So this is going to have 3 links in the chain. So we're going to have dy dx. You start to get better and better each time. You know, this becomes second nature, but this is why you're taking 124 to get better at this, one of the reasons. So you need to know the derivative of arctangent. The derivative of arctangent is a kind of a weird one. So let's write it blah. The derivative is 1 over 1 plus blah squared. So that one's kind of surprising. So the first thing you're going to write here is 1 over, it looks so different than the function you started with that this one often throws people off. But that's the derivative of the tangent piece. Put a little dot here, and you just have to have this organized way of thinking. So then you say, whatever was in here needs to be my input here. So this one looks funny, log of x cubed plus 5. And then you're like, okay, now I'm done with that. And then I need to do the derivative of log. So think about how you're going to finish this. The derivative of log of blah is 1 over blah. So 1 over x cubed plus 5 times, and then you erase that. (3x squared). Now, usually when we have a fraction like this, we just move it up to the top because it just looks prettier. All right, let's go find a linear approximation. In fact, let me think for a second. So when I was making exam 2 review videos, I never got to it. This is the next video I was going to make. Yeah, I found some questions. Well, that's the one I found. Linear approximation itself is a fancy way to say find the tangent line. A tangent line is a linear approximation. It's one of the most valuable things about tangent lines, and it's used to do a bunch of stuff. So if you have some crazy messy function, sometimes it's useful to find the tangent line at a given spot and use the tangent line instead of the function. Here's one cool application of that. It turns out if you find the tangent line and then find where the tangent line intersects, and then go to that point and find another tangent line and find where that intersects, and you keep doing it, that's called Newton's method. And that's one of the techniques to find the solution where the function is zero. So this idea of approximating with tangent lines is an important idea. In fact, if you look at most scientific papers, they use what are called linearizations, meaning I have something too complicated to study, so I'm going to replace it with a line, because a line is easier to study. Now, in doing so, I'm making assumptions. But a tangent line is a good approximation near a value. That's this idea. The question itself, though, is asking you to find the tangent line. So I think of this as, all right, I know how to find a tangent line. It looks like this. I need an x value, I need the y value, and I need the slope. The x value they gave us, the y value we get by plugging into the function, the slope we get by plugging in a half. That's what the question's asking you to do. The linear approximation step is just one additional step at the end, which says use it. And what this is saying is that whatever we get out of this is going to be pretty close to whatever we get out of this. That's the idea of a linear approximation. The further you get away, so if you zoom in on a tangent line, it hits your graph and zooms past it. If you're standing somewhere near that point, they're really close to the same value. If you get further away, they're not close. That's this idea, which seems weird. People are like, why didn't you use the exact value? There's a lot of situations when you're analyzing something and you don't know the numbers, you're just trying to do a general analysis, and you really have to linearize it or we can't even work with it. So that's this idea. Here you could just plug it into your calculator. All right, so this question is really just asking you to take the derivative. So what is the derivative? Yet another try. This is just introducing you to another application of derivative. So arctangent looks like this, 1 over 1 plus something squared. And what goes here? Just to see if you're with me. (2x). So most things on this test will involve just taking a derivative from the get-go. Times the derivative of the inside, so what goes here? 2, lovely. Plus, now we're going to do this term. What's the derivative of log? It's 1 over 8x cubed times the derivative of the inside, which is 24x squared, because 3 times 8. And that simplifies a whole bunch, I think. 24x squared over 8x cubed. Well, I think it's just 3 over x. That's kind of weird. So this is going to be 2 over 1 plus, I feel like I want to simplify this. I don't know why. Plus 3 over x. And so to finish this question, we would need to plug in a half here, and here, and here, and here. I imagine since this is an exam question, that must actually simplify. So for example, it's going to be arctangent of 1 plus log of 1, I think, because it's going to be 8 over 8. So here's a question for everybody. What is arctangent of 1 plus log of 1? That's going to be the value. That's what's going to go here. The height. In the end, I always tell students to remember the function gives you the height, the derivative gives you the slope. If you can just remember that, that often helps you in a lot of problems. And it helps justify why you're even doing this. But this is going to be pi over 4. So arctangent log of 1. And then we need to plug in a half here. 1 plus 6, it's 7. I'm just trying to get to a point where I have this. So when all is said and done, we get the following. The tangent line is 7. Let's just assume this is right. We call that the linear approximation. And these two things are very close to the same value if you're near a half. So the way you finish this question is you plug in 0.51 here into your calculator, and that's your answer. So the point of me getting that far is I wanted to show you a linear approximation question is really asking you, take the derivative and give the tangent line. Okay, we're going to wrap that up. Thanks for being here. Hope that was helpful. I don't know what will happen for the final, whether I'll be able to do such a thing, but good luck on your midterm. I hope you'll do practice some more exams. Check out my YouTube channel. And hopefully I'll see some of you in the summer taking 126. That would be nice. All right, take care. How do I close this thing? Stop. Close.